In the last two lectures, we saw some preliminary results, some tools from calculus that will help us in understanding the topics in this course, and that will also help us in developing some numerical algorithms. We also saw an overview of the topics that we would be studying in this course, and we said that we shall begin with the topic on polynomial interpolation. So, we shall see what we mean by polynomial interpolation and how we can reconstruct a function whose values are known at a set of discrete points with the help of polynomial interpolation, or how we can obtain an approximation of a function whose values are all known in a closed interval, which again can be obtained using interpolation polynomials. So, let us mathematically formulate this problem and see how we can develop the interpolation polynomials that approximate a given function. So, let us formulate the problem first. So, we are given a set of discrete values, say at points x naught, x1, etc., xn, and the corresponding values are say y naught, y1, y2, etc., yn of some function y is equal to f of x, say which is y of x. Either the function values are given at these points and we do not know what the function is, we want to reconstruct the function f of x, or we know this function f of x in some closed interval and we would like to approximate this function say by a polynomial, in which case we choose some n plus 1 points and list the set of values xi, yi. So, we seek a polynomial say of degree at most n passing through these n plus 1 points such that p n of x approximates the function f of x such that p n takes values yi, namely f of xi at the points xi for I equal to 0, 1, 2, 3, etc. n. So, the problem is to seek a polynomial p n of x of lowest degree possible that interpolates the function f of x at a set of discrete points such that p n of xi is yi for I equal to 0 to n. So, this is the problem that we would like to address now. So, the question is, does there exist such a polynomial? What happens if suppose I am given say information at one point x naught, y naught, namely n is equal to say 1. Then in that case, yes, the construction of a polynomial is obvious. So, I can take a polynomial say p naught of x to approximate the function such that it is the constant function. Say suppose I call that constant as say c naught. What should be the value of c naught so that the polynomial satisfies the given condition? So, I want p naught at xi or that x naught to be equal to y naught. This immediately tells me that my c naught is y naught. So, my constant polynomial that approximates this function is p naught of x is equal to y naught. That is fine. What happens say if n is equal to 2? Let us understand first. When n is equal to 2, we are given information at 2 points x naught, x1, corresponding values are y naught and y1. Say these are the 2 points. Then I want a polynomial. So, given 2 points, I can fit a straight line passing through these 2 points. so that I can look for a linear polynomial of degree 1. So, in this case I can construct a function p1 of x of degree 1 that approximates the function f of x with the property. So, let us write down this polynomial. I shall take this polynomial as c naught plus c1 into say x minus x naught. It is a linear polynomial. What should be the property that should be satisfied by this polynomial? It is such that p1 at x naught must be y naught and p1 at x1 must be y1. So, this gives you that c naught at x naught, this factor will vanish. So, c naught is y naught, right, and if the condition p1 of x is equal to y1 should be satisfied, then it means that y1 is equal to c naught, that is y naught, plus c1 into x minus x naught. So, that immediately gives us the constant c1 to be y1 minus y naught by x1 minus x naught. So, c1 gets determined. So, what is the polynomial that approximates this function f of x? It is c naught, which is y naught, plus c1, which is y1 minus y naught divided by x1 minus x naught, that is c1, into x minus x naught, and that is a first degree polynomial that approximates this function f of x, and it interpolates the function at a set of discrete points, namely x naught, y naught and x1, y1. So, we see that once we know that the 0th degree polynomial exists, the first degree polynomial can also be constructed and it exists. So, one can continue now by taking n is equal to 3. So, there are 3 points which are given to us, x naught, y naught, say x1, y1 and x2, y2. So, passing through these 3 points, I must have a curve in the xy plane that is going to approximate the function f of x. So, that the equation of this curve is going to be a second degree polynomial. Let us denote it by p2 of x. So, that f of x is approximated by p2 of x, which is a second degree polynomial or a parabola passing through these 3 points. So, what is its equation? I can take the equation of the parabola to be c naught plus c1 into x minus x naught plus c2 into x minus x naught into x minus x1. And you should see that the c naught plus c1 into x minus x naught is essentially this p1 of x. So, what have I done? I have added an extra term, right, to p1 of x and construct a polynomial of degree 2, namely p2. That is what I did here. To get p1 of x to p naught of x, which is c naught, I added this term and I am able to show that this p1 of x satisfies my requirement. Now, to get p2 of x, I add to p1 of x a term, so that I am going to show that p2 of x is going to satisfy the properties that we want. So, what do we want? We want p2 of x naught to be equal to y naught, p2 of x1 should be y1 and p2 of x2 should be equal to y2. So, there are 3 conditions to be satisfied and we have 3 constants c naught, c1, c2 to be determined, and these 3 conditions will give us a polynomial which is p2 of x after determining c naught, c1, c2 subject to these conditions, which is a second degree polynomial. So, we can continue in this way and construct higher degree polynomials given n is equal to 4, p3 of x, etc. So, that finally given n plus 1 points namely xi comma yi for I is equal to 0 to n, we can get a polynomial Pn of x of degree n that interpolates the given set of points, data points. We have shown that it is possible to get polynomials of appropriate degree depending upon the information that is available to us. So, the question that arises is, yes, by constructive proof we have shown that one can get a polynomial that interpolates a given data. The question now is this polynomial a unique polynomial that interpolates the given data? So, we would like to now give a result that shows that a polynomial does exist having this property, and that this polynomial so constructed is a unique polynomial. So, we present this result in the form of a following theorem. So, the result is as follows. Let us call this as theorem 1.1. So, it says given x naught, x1, etc., xn, or if x naught, x1, etc., xn are real distinct numbers, then for arbitrary y naught, y1, y2, etc., yn, there is a unique polynomial of degree at most n, say Pn of x, such that Pn of xi equal to yi for I is equal to 0, 1, 2, 3 up to n. So, given n plus 1 distinct points x naught, etc., xn, for any arbitrary values which are associated with these n plus 1 values, namely y naught, y1, etc., yn, the result says there is. So, that is says there exists a polynomial, and this polynomial is a unique polynomial. What is its property? It satisfies the condition that it passes through the points xi, yi. So, Pn of xi equal to yi. Let us prove the uniqueness part. So, we want to show that there is a unique polynomial, one and only one polynomial that has this property that interpolates the set of discrete data points. So, let us assume on the contrary, if suppose there are two such polynomials Pn and Qn of degree n, such that Pn satisfies the condition Pn of xi is yi, and Qn also satisfies the condition Pn of xi equal to yi for I is equal to 0, 1, 2, 3 up to n. So, let us call by Rn Pn minus Qn. So, Pn and Qn are polynomials of degree at most n, and so Rn, which is difference between these two polynomials, is a polynomial of degree at most n. At most n. Then what other property does Rn satisfy? Let us see. If I evaluate Rn at the xi, then Rn of xi is Pn of xi minus Qn of xi. But I know Pn of xi is yi and Qn of xi is also yi. So, Rn of xi is 0 for I is equal to 0, 1, 2, 3 etc. up to n. So, we know that Rn is a polynomial of degree at most n and Rn at xi is 0 for I is equal to 0 to n. Now, Rn being a polynomial of degree at most n, it can have at most n zeros if it is not the 0 polynomial. So, let us write down that result. Rn being a polynomial of degree at most n, it can have at most n zeros if it is not the 0 polynomial. If it is not the 0 polynomial. But what have we seen about Rn? What is the property that we know about Rn? Since x0, x1 etc. xn are n plus 1 distinct points, and Rn of xi is 0 for I is equal to 0, 1, 2, 3 etc. n, it is clear that Rn has n plus 1 zeros. What are its zeros? They are x0, x1 etc. xn, it has n plus 1 zeros. But what do we know about Rn? Is a polynomial of degree at most n and it can have at most n zeros if it is not the 0 polynomial. Here we show that Rn has n plus 1 zeros. So, Rn has to be the 0 polynomial. So, Rn must be identically 0, that is Pn minus Qn must be 0, or this implies that Pn must be identically the same as Qn. So, which shows that there is a unique polynomial of degree at most n, say unique polynomial Pn of x of degree at most n, such that Pn of xi is equal to yi for I equal to 0, 1, 2, 3 up to n. So, you will be able to determine a unique polynomial that interpolates the given set of data points. So, the uniqueness part of the theorem has been proved. So, we now move on to the existence part, and the existence is through construction of such polynomials as we have already indicated. So, we shall use induction to show the existence part of this proof. We first show that there exists a polynomial of degree 0, and if we have a polynomial of degree k that satisfies the given property, then we show that there exists a polynomial of degree k plus 1 satisfying the property, and hence by induction the result is true for all n, and the proof is complete, and thereby we would have shown the existence of such a polynomial that interpolates the function. So, let us start with n is equal to 0. So, for n is equal to 0, the existence is obvious in the sense that since a constant function p naught, namely a polynomial of degree less than or equal to 0, can be chosen such that P naught of x naught is y naught. Suppose that we have obtained a polynomial. We have obtained a polynomial of degree less than or equal to k minus 1 with pk minus 1 of xi equal to yi for I is equal to 0, 1, 2, 3 up to k minus 1. So, given information at k points, you can find a polynomial of degree k minus 1 that interpolates at these points xi, yi. So, suppose that we have already obtained a polynomial of degree less than or equal to k minus 1 satisfying this property. So, this is our induction hypothesis. So, what should we show? We should show that we would be able to obtain a polynomial of degree k less than or equal to k satisfying pk of xi equal to yi. We now construct, we now try to construct pk in the following form, namely pk of x is equal to pk minus 1 of x. I recall what we did in the beginning of this lecture. Having constructed p naught, we constructed a polynomial of degree 1 by taking p1 of x to be p naught plus a constant times x minus x naught. So, how did we construct p2? Having constructed p1, we can now construct p2 such that p2 is p1 plus c1 into x minus x naught into x minus x1. Given the information at 3 points x naught, y naught, x1, y1, x2, y2. Simply extend that idea. Having constructed pk minus 1 of x of degree less than or equal to k minus 1, take the polynomial pk in the form pk of x is pk minus 1 of x plus say some constant, arbitrary constant a, which we will have to determine, multiplied by x minus x naught into x minus x1 etc. x minus x k minus 1. Let us see whether this construction works. How do we ensure that this construction works? We must show that pk satisfies the condition that pk at xi is yi for I is equal to 0, 1, 2, 3 up to k. So, let us first check what happens at the xi. So, it is pk minus 1 of xi plus I shall take my I to be any one of 0, 1, 2, 3 up to k minus 1. So, when x is xi for I between 0 to k minus 1, I observe that it has factors x minus xi for I is equal to 0 to k minus 1, and therefore, this will give you 0. So, pk of xi is equal to pk minus 1 of xi, but I know pk minus 1 of xi is yi for I is equal to 0, 1, 2, 3 up to k minus 1. So, my polynomial pk satisfies the condition that at points x0, x1 etc. xk minus 1, it interpolates the function by satisfying the condition that pk of xi is yi. But what do we want? We want this polynomial to be such that pk of xk must be yk. So, we impose that condition. So, pk of xk must be equal to yk, which implies that yk is equal to pk minus 1 of xk plus a times xk minus x naught, xk minus x1 and so on up to xk minus xk minus 1, which immediately tells you that a, the arbitrary constant, must be yk minus pk minus 1 at xk divided by xk minus x naught into xk minus x1, etc. up to xk minus xk minus 1. So, the constant a is determined, and so we can substitute here and write down what the polynomial pk of x is of degree k. So, that must be equal to pk minus 1 of x, which is already known, you have constructed, plus a is yk minus pk minus 1 of xk divided by xk minus x naught into xk minus x1, etc. up to xk minus xk minus 1, right. This multiplied by the factors, namely x minus x naught, x minus x1, etc. x minus xk minus 1, x minus xk minus 1, and you observe there are k such factors, and so the leading term will be x to the power of k. So, your polynomial pk of x is a polynomial of degree k minus 1 plus a term involving this constant multiplied by some factors whose leading term is x to the power of k. So, you have constructed a polynomial of degree k that interpolates the function at a set of points x naught, x1, etc. xk. So, they are k plus 1 points. So, pk interpolates the function at a set of k plus 1 points x naught, y naught, x1, y1, etc. xk, yk. So, assuming that pk minus 1 has been obtained, we have been able to construct a polynomial of degree k. So, the result is true for all n by induction. So, pk of x is this, and we have shown pk of xi is yi for I is equal to 0, 1, 2, 3 up to k. So, therefore, by induction the result is true. The result is true for n. What does that mean? That means there exists a polynomial of degree at most n such that Pn of xi is equal to yi for I is equal to 0, 1, 2, 3 up to n, and that is what we wanted to show. Given n plus 1 real distinct numbers for arbitrary values y0, y1, etc., yn associated with these x naught, etc., xn, there exists a unique polynomial of degree at most n satisfying this condition. The polynomial so constructed is called an interpolation polynomial that interpolates the function at a set of these n plus 1 discrete points. So, now we have answered this question. Yes, there exists a polynomial, and this polynomial is a unique polynomial satisfying the condition. So, the next question is, okay, how are we going to get this polynomial? If there are 2 points, it is easy. 3 points, yes, with some computations we can get this polynomial. When the number of information given to us becomes more and more, in practical applications this is what will happen. We will have information about a function to be constructed at a set of several points, and going one by one taking a third degree polynomial, then constructing the fourth degree polynomial, etc., is going to be a tedious process, and therefore, we would like to get some simple methods by means of which we should be in a position to construct this unique polynomial for a given set of discrete data. So, let us see how we can do it, and finite differences is going to be an important concept that is going to help us in construction of interpolation polynomials, and let us see what one understands by finite differences.